Hi folks, Mr. Ackerman here. Thanks for watching. The topic of today's video is gravitational potential energy and kinetic energy. And in this video, we're actually combining two sections from the book and therefore two lessons in the homework schedule, as you can see below. What we're going to get to see today is two of the effects that work done on an object can have. In one of the examples, you're going to see how the work done on an object can cause it to rise up to a higher position above the ground than it was before the work was done, and therefore gain something we call gravitational potential energy. And in another example, you're going to see how the work done on an object can cause it to speed up and therefore increase its kinetic energy. I'm also going to show you two important results, or rather applications, of these two kinds of work, which I hope will allow you to see the importance of understanding work as far as our daily lives are concerned. So take a moment to pause the video and have a look at the questions that we're going to address, as well as where we are in the unit schedule, as well as what the learning goals and success criteria are. And when you come back, we will begin. Okay, you're back and we're ready to start here, so let's take a look at our first slide, the idea of using work to calculate something called the gravitational potential energy. So first of all, I want you to look around you and find something that you can grab onto and pick up. This could be your pencil case or a book or something like that. What I want you to do is start with it at the desk or on the ground or wherever you are, and just lift it as slowly as you can. I don't want you to throw it up in the air or anything. Just lift it with sort of the least amount of effort that you can. What do you notice? As you lift it, start thinking about the amount of force you have to apply. And I think you'll start to think in terms of a physics terms that what you're doing is applying just a little bit more than the force of gravity to get that object moving. And then once you've got it moving up to a certain height, you can stop. Now think about what you've done. You've taken the object, and let's say you were down on the ground here, you're standing, and you grabbed onto an object, which I will call M, a mass. You exerted a force in the upward direction, and like we just said, this force has to be at least equal to the force of gravity. So I'll write here that the applied force that you used, the magnitude of that, is equal to the force of gravity, which of course is mg. And what you did was you lifted it up to a certain height, whatever that height may be. Let's call that delta d, a distance that you moved it. And so let's calculate the work that you did. Well, work, of course, is equal to the magnitude of the force you used times the cosine of the angle between that force and the displacement that you caused. Now, since the force is at least equal to the force of gravity, we get to use mg. The force and the displacement here are in the same direction, so the angle theta is equal to 0 degrees, and therefore we can put in cos 0 in here. And the delta d, of course, we can just write delta d, but allow me to write delta h here. And the reason I want to write delta h is to remind you that we are lifting the object to a greater height. And that way I can put in the following: mg cos theta, cos 0 rather, delta h. Now, from math class, you know that the cosine of 0 is 1. So what we really have here is mg delta h. And this then is the formula for the amount of work that you do when you lift an object from one place to another. Now, when you do this, what you've actually done is increase its gravitational potential energy. And therefore, what we sometimes do is call this, instead of work, we might call it E, gravitational. However, it's not exactly the gravitational energy, it's rather the change in the gravitational energy. You see, the object, when it was down here, it had gravitational potential energy. For example, it looks like the guy was holding the object a little bit above the ground. He could have dropped it down like that, and it would have hit the ground. Maybe it would have landed on his toe and hurt him. It would have had some energy. So it had gravitational potential energy already compared to the ground. What he did was he changed its gravitational potential energy. So we use the delta symbol and we write it as mg delta h. Now, another thing you can do here is you can remember from mathematics and from science, anytime you see delta, you think change, you think final minus initial. So what you could write here is Eg final minus Eg initial is equal to mg, and there is a delta again, so this will be H final minus H initial. And of course, now you can multiply into the bracket there. You can expand that bracket, mg H final minus mg H initial. And so here's what you've got. Let me just copy this side down one more time to make it easy to compare. You've got Eg final, the final gravitational potential energy, was mg H final. And Eg initial was mg times the initial height. So sometimes you'll see people say, oh, that means that Eg is equal to mgh. And that's fine too. You can write this if you want. Eg equals mgh. But quite often what we're concerned with is the change in gravitational energy. And why is that? Well, we're going to see in a minute. Let me show you an example. Here's a picture from your textbook. The textbook is Physics 11 by Addison Wesley, and it shows a bunch of nails that are just starting to be hammered into a piece of wood. There's a plastic tube, and there's a bunch of nuts and bolts here. And the idea is, I mean, you could try this if you wanted to build it. The idea is to know a certain amount of mass made up of these nuts and bolts. You're going to drop that down onto the nail. And I think you know what's going to happen. It's kind of like hammering nails into wood. If you drop this down, the nail will be driven somewhat into the wood. Now the question is, how far will it be driven into the wood? Well, I guess that depends on how far this falls and how fast it's moving when it hits the nail. For example, if we allow this nut and bolt combination to fall a certain height, a delta H, and if it has a certain mass, we now have a situation where gravitational energy has been lost because we're going down. And therefore, we lose gravitational potential energy. What's going to happen when we drop this? I think you know it's going to speed up. Therefore, it's going to gain something that we've already called kinetic energy in this course. So we're going to have a little conversion of energy here from gravitational into kinetic. And so at the bottom here, the nuts and bolts will be moving faster than they were at the top. They will hit the nail, and now they will drive the nail into the wood. Maybe the nail will be driven down to here, and it will move through a certain distance, like that. Well, if that's the case, then think about what has just happened. The nuts and bolts will have exerted a force downward onto the nail, and there will have been a displacement. In other words, work will have been done. It would be an F, cosine 0 in this case, delta D. So the reason we use the word potential when we're talking about gravitational energy is because way up here where the nuts and bolts started, unless we let go of them, they won't do this nailing of the nail into the wood. It's only once we release them that they pick up kinetic energy and then do work when they strike the nail. In other words, way up here they have potential to do work, but they don't realize their potential until we let go of them. So this is why we call this gravitational energy potential energy. There's also one other thing I want you to consider, and this is the idea of what's called a reference point. Let me explain. Imagine if we were to do this as a little lab in school. And now in the school that I teach at, the physics room is on the first floor. So imagine if I did this on the first floor. Of course, it's the ground floor. So maybe down here, the height, you could say, is 0 meters above the ground. And how high would we lift this? I don't know, maybe we would lift it something like 1 meter above the ground. All right, well, imagine if at the same time that I was teaching physics, someone upstairs decided that on the second floor, she was going to teach the same lesson in physics, just in a different classroom. Well, she wouldn't be at the ground level. She would be, let's say, starting with the ground on the second floor. I don't know, maybe it's 3 meters above the ground. And therefore, as this teacher lifts up these nuts and bolts, they will be a meter above that, 4 meters. Now here's the question I have for you. would she observe anything different than what I would observe? I think you know that there's really not going to be any difference if you repeat this experiment on one floor versus the other, and therefore it's not really important in an absolute sense how high you are above the ground. What matters is the delta H, the amount of change in height. And that's why the formula back up here that we use has mg delta H, not the exact height that you are above the ground. So when you're solving one of these problems, since it doesn't really matter where you are in an absolute sense, what we do is we set a point in the problem where h is equal to 0. And this is usually done at the lowest point in the problem. So when you're solving any problem involving gravitational potential energy, you have to, before you start solving it, look for where is the lowest point that anything is going to happen in the problem. And that's where we set the h equals 0. So for me on the first floor, the lowest point is the ground, let's say. So I'm going to call that the h equals 0 point. And my colleague upstairs who's teaching this lesson, she can do the same. She does not have to go and say, oh, how high am I above the first floor? She can call this 0 for her, and therefore this 1 meter. She's going to get the same results in her calculations as I am. So this is what we mean by a reference point. If you go below the reference point for whatever reason, then you can have negative height. That's fine too. So I'll write that in here. Negative height equals below the reference point. So keep that in mind. It's going to be important when we talk in terms of gravitational potential energy, and also when we get to solving more challenging problems. Here's an interesting problem coming up. It's a real-life example involving gravitational potential energy, and it's a way that we generate electricity, especially in the province of Ontario and Quebec. This is a picture of a hydroelectric power plant, a hydroelectric dam, if you will. And I believe, if I'm not mistaken, this one looks like the one on the Niagara River. If you go to Niagara Falls from Toronto, let's say, on the way there, drive through Niagara-on-the-Lake, a nice little town that is just before Niagara Falls, and take the road along the river, and you will drive right over top of this dam. You might not even realize that you're on top of it until you notice all of the electric power lines, and you look down and realize, oh, I'm on this huge concrete structure. Well, what exactly is this? You can see there's water up here at a higher point. Let me just change the color so you can see a bit better. There's water up here, which is actually water that has been diverted from Niagara Falls. Instead of going over Niagara Falls, it's been diverted to fill up a large reservoir just behind the dam. And then what it does is it flows down through the dam, and you can see this from the roadway. There's actually one of these on the American side and on the Canadian side. So it's really kind of neat that if you're driving on the American side, you get to see the Canadian dam. And if you're on the Canadian side, you get to see the American dam. Both of us are generating electricity. What are we doing? We're letting the water fall down. You can see the water coming out down here, making the waves there. And somehow, this water, just like the nail or the nuts and bolts in the previous example, this water has lost gravitational potential energy, which has converted, of course, to kinetic energy. And just like the nuts and bolts applied a force through a distance on the nail and therefore drove it into the wood, what's going to happen here is the water is going to spin a turbine, which is like a big water wheel, and that will be attached to an electric generator, and that will generate electricity. So here's a diagram that shows this. This diagram, if I recall, is from Ontario Power Generation. They offer this. The picture here you see is from just a Google image search. And what you can see is that the water comes down through these gigantic pipes called the penstock in the dam. At the bottom is a turbine that they spin, and the turbine is attached to a generator, which is connected to the electric power lines, and that energy is carried to your home. It is supplied to your home. And you are probably using energy generated in this way right now. We can't, of course, tell exactly where every joule of energy came from, but there's a very good chance that some of the energy you're using right now in your home came from hydroelectric power generation. Here's a question for you. How much energy can we generate this way? Well, we might do a little calculation. For example, if we were to calculate how much Eg a kilogram of water, let's think of 1 kilogram of water. That would, by the way, be 1 liter of water. Let's think about how much gravitational energy 1 kilogram of water has at the top of this dam relative to the bottom. So we would say mgh at the top is the gravitational energy of a kilogram of water, but we have to compare that to the gravitational energy at the bottom. So that'll be mgh at the bottom. Now remember, we are allowed to set the reference point to be 0 wherever we want. We can set h equals 0 at the lowest point in the problem. So that's what I'm going to do right here. I'm going to make h equals 0 right down here because it's going to make my calculations easier. It's going to cause something to be 0 in this question, and therefore there's nothing to calculate. So really what I get is just for 1 kilogram, like we said, I'm going to put in a 1 for m, I'm going to put in a 9.8, and now I got to know the height. Now, I don't know exactly the height, but just estimating it, I'm going to guess, I don't know, maybe 50 meters, let's say. I'm probably wrong, but I don't think I'm too wrong here. And since we're estimating, I'm not even going to bother taking out my calculator. I'm just going to say approximately. Let's call that 1 times 10 times 50. So 500 joules of energy. And so there you have it. If I could somehow convert all of that gravitational potential energy directly into electric energy, then each kilogram, each liter of water that goes down through those penstalks could supply me with 500 joules of electrical energy. Of course, that never happens exactly. The water, as it goes through, is going to rub against the sides of the penstock. There will be some friction. Even as I turn the turbine, there will be friction. A lot of heat might be produced as the generator spins, and some noise will be produced. So I'm never going to get all of that energy to become electrical. In fact, even when the electricity is transmitted to our homes, the wires carrying it will heat up, and so now I'll lose some of the energy due to heating. By the time this gets to my home, I may never get the full 500 joules of energy for each kilogram of water. I don't know exactly what percentage I'll get, but at least I'll get some, and one of the beauties of this method of generating electricity is there will be no air pollution. There won't be any carbon dioxide or other pollutants released into the air like there are when we burn fossil fuels. On the other hand, there is an environmental drawback. We will have to flood the land behind the dam. We will have to alter the flow of the water through this part of the river, which may affect marine life in the river either down here or up here. And you may argue that this is not a very beautiful sight as far as it fits into the natural environment. But I guess there are always trade-offs in life, and these are some of the ones we have to consider when generating electricity. All right, moving along. What we're now going to look at is using the concept of work to calculate the change in an object's kinetic energy. If you remember back here, we looked at how work could be used to calculate one type of energy, gravitational potential. And by the way, I just realized I almost forgot, that was the fact of the video. The fact of the video is this formula, which I want you to remember, and the idea of a reference point. So please don't forget that if there's a quiz in class on the fact of the video. This is the formula for the change in gravitational energy, and we have to use the reference point always. Now we're going to look at another way that work can affect an object in terms of changing its kinetic energy. And this, by the way, will be the second fact of the video. 2 sections here, so 2 facts. Let's take a look. When you apply a force on an object, sometimes you can raise it up, like we talked about here. Sometimes it can fall down, like we talked about here. However, that's not always the case. I'd like you to consider the following. Imagine you go and maybe you go skating, for example. And so what you might do is, when you're skating, of course, we're often dealing with a frictionless surface. So imagine taking an object like a curling stone, for example, and applying a force in the forward direction on that curling stone. Let's call this the applied force. Okay? And you're going to apply a force over a certain distance. So maybe we start here, whoops, want to make a straight line there. Start here, and we apply that force and allow the curling stone to move a certain distance like this. Okay? How much work do we do on the object? Well, of course, we do work equal to F cos theta delta d, where theta is the angle between the applied force and the displacement. Now, these two are in the same direction, so theta in this example is 0. So once again, we have cos theta is cos of 0, that's equal to 1, so we just have F delta d as the work done. Okay? However, there's something else we can write here, so I'll do this in a different color. Because you are applying force forward, and because I've asked you to imagine that you are on ice, which for our purposes will mean no friction, and because gravity downward will be cancelled by the normal force upward, it's pretty easy to see that in this case, the applied force will also be the net force. So watch what I can write here. I can take this formula for work and do the following. I can sub in for F net, and keep delta D. Now we know from Newton's second law, F net is equal to ma. So now we have ma times delta D. We also know that A is equal to V final minus V initial divided by time. That's the acceleration formula. And here's delta D. Now, we're going to do a little mathematical trick here. I'm going to group these two. So delta D over delta T, if you recall, is V av. Okay? Also, if I push on an object with a certain net force and I get a constant acceleration, I can also write that V av is equal to V1 plus V2 divided by 2. This, if you recall, is a formula for the average velocity when you're dealing with constant acceleration. Because the force is constant here, this is constant acceleration. So now look what happens to my formula. I'm kind of running out of room here. I'll try to continue here. I've got m, still got the V2 minus the V1. But now my delta D and delta T have turned into a V1 plus V2 divided by 2. Now what can I do here? Well, first of all, the 2, you can just slide that over here, so you end up with the m and the 2 in the denominator looking like this, 1/2 m. And then here you're going to have two brackets, so you're going to multiply these out. This times that, this times that, this times that, this times that. What are you going to get? Let's have a look. The V2 and the V1 give you this, V2, V1. The outer terms will give you V2 squared. I'm running out of a little bit of room here, so just give me a moment to shrink that down and move things over. All right, there we go. Let's continue. We have V2 times V1. We've got V2 squared. Here we have minus V1 squared. And in the end, we have minus V1, V2. Now you'll notice I've dropped the vector hats, and that is something you can do when you're multiplying vectors. We don't talk about multiplying vectors until grade 12 math, so for now take my word for it. I wouldn't lie to you about something like this. V2, V1 minus V2, V1, they cancel, and it leaves me with V2 squared minus V1 squared. So I've got this. And if I expand this out, I've got 1/2 mv2 squared minus 1/2 mv1 squared. That is equal to the work done. Remember, we started way up here with work done. The work done when you apply or when you exert a net force on an object through a distance across a level surface, what does that work do? Well, it changes something dealing with your speed. In fact, these terms here are what we call kinetic energy. And if you look at what we have, this is a 1/2 mv final squared, and this is a 1/2 mv initial squared. When you have a final something minus an initial something, we call it a change. Well, this is actually what we call EK, kinetic energy final, This is kinetic energy initial, and what you've actually calculated here is called the change in kinetic energy. In other words, work has been done to change the energy of movement. And there you go. There's another example of how work can affect an object. In this example, we are saying that something called the kinetic energy is equal to 1/2 mv squared. And it can have a final value, it can have an initial value, but if you do work on an object, that very well might change its kinetic energy. So let's see if we can fit this all onto one screen. There we go. Let's take a look at a quick example of this actually happening. I'd like you to have a look at this diagram here. This diagram again is out of your textbook, Physics 11 by Addison Wesley, and the diagram is meant to illustrate that if you took some clay or some plasticine and you took 3 different balls and you dropped them into the clay, what would happen? Well, of course, they would probably create a dent. So this is a neat activity that you could actually try at home. You could take 3 different balls, maybe one of them would be light, maybe one of them would be medium, and maybe one of them would be heavy. And you could lay out some plasticine nice and neat and level and drop each one, but you'd have to drop it from the same height above the ground in order to have a fair comparison. What do you think would happen? Pause the video for a moment and predict what would happen when each of the balls hit the clay. Okay, and you're back, and I think we all know that the light one will cause a small dent, the medium one will cause a bigger dent, and the heavy one, who knows, maybe it'll dent all the way to the floor. So right here, you're using a ruler to measure the depth of the dent that each ball causes. This is an example of the gravitational energy that we discussed earlier converting to kinetic energy, but then the kinetic energy causing the object to exert a force through a distance. In other words, you've got in here a delta D, that was the result of a force, that is work done, and so voila, work and kinetic energy are in fact related, and this is the formula that relates them. Memorize that formula. It is fact number 2 of this video. And we're going to see an example of that as we finish off on the last slide here. An example involving kinetic energy, and this one very serious. I know the first example I showed you here was important for you to know because it's important to know about electricity, but this one is important for your safety. I've shown you a picture again from Google Images of a car that's been in a very bad accident. From a physics standpoint, what has happened to this car? You can see, obviously, a force has been exerted inward on the car. We use the letter F to symbolize that. And it has caused the car to indent. In other words, it has caused a displacement to occur. There it is again, force and displacement. In other words, work was done on the body of this car. Hopefully it didn't injure the passenger too badly. Work was done. Using the idea that we just learned here, that work comes from a change in kinetic energy. Let me show you what I mean. Suppose the driver of this car was driving along at a speed of 30 meters per second, which is kind of like Highway 401 speeds. And let's suppose this was V1, so let's suppose the final speed, of course, was 0 due to being in an accident and the car coming to rest. Now, if we also assume that the car has a mass of, just to keep things simple, let's do 2,000 kilograms, a nice round number, then I can calculate the initial kinetic energy. What's that going to be? EK1 is a half m1 v1 squared. That's a half of 2,000 kilograms times 30 meters per second squared. And once again, I'm running out of room here, so just move things over. There we go. That's going to equal a half of 2,000 is 1,000. 30 squared is 900. So that's going to be 900,000 joules of energy. That's the kinetic energy that this car had when it was moving along before the collision. Of course, in the end, the kinetic energy would be zero because the car came to rest. Now, why did the car come to rest? Let's analyze this from the point of view of forces. Driving along in the car, and obviously this car hit something. I don't know if it hit a pole or a wall or another car, but obviously it hit something. Let's imagine that the car hit a pole, a utility pole. So the car was moving this way in the beginning. Why did it stop? Because when it got to here and made contact with the pole exerted a force in this direction. So this was the force exerted by the pole on the car. Now, while that was happening, the car continued to move forward a certain distance. That, of course, is why you see that the car is all dented here. Here again we see force and distance. That means work got done. How much work got done? Well, let's calculate. The work was equal to F cos theta delta D. But look at the diagram here. The force is backward, causing the car to slow down. The displacement was still forward as the car drained off its speed. What is the angle? It's 180 degrees. They're going in opposite directions. So this time, whatever that force was, we're going to multiply by cos 180, and we're going to write down the distance over which the car stopped. Now, in a very bad collision, you might actually just crumple completely the front of the car and stop. Maybe that would be a 1 meter stopping distance. If you stopped over a distance of just 1 meter when going at highway speeds, you would be in for a very, very serious situation there. So let's hope that the distance wasn't 1 meter, but since that might be what this picture suggests, let's just put it in anyway. So what have I got here at the moment? I've got F times cos 180, which is -1, times, and I'm going to estimate 1 meter. The car basically drove right into a pole and came to a stop. Now, that's the work done, and as we learned previously, the work done equals the change in kinetic energy. So let's plug this all in. If we look at our initial and final kinetic energies, what is the delta EK? Delta EK, anytime you see delta in math, you do final minus initial. So that was EK final minus EK initial. The final kinetic energy was 0 minus the initial kinetic energy of 900,000 joules. That gives you a negative 900,000 joules. And that's supposed to be equal to the work done, which, as we see here, is F, the force, times cos 180, which is -1, times the 1 meter that I estimated here. So that's just going to be negative F. Look what happens with the minus signs. They, of course, will cancel out. The reason that we had a negative here was because the force was acting opposite the displacement. The reason we had a negative here is because the car was slowing down. It was losing kinetic energy. The delta was negative. In any case, in the end, this allows me to calculate the force on the car, 900,000 newtons of force. That's a lot of force, and like I mentioned to you before, I doubt that this is exactly correct. I'm just sort of using the picture here and making a rough estimate. I don't know for sure that the car stopped over a 1 meter distance, but that's a lot of force. And in terms of your safety, that force is going to be exerted on the objects within the car as well. That includes you. So when you are driving, you have to be careful how fast you go. Obviously, we know if you go faster, a crash is going to hurt more. But from a physics standpoint, it's actually more serious than that. Look at the formula that we used to calculate the 900,000 number. It came from a half mv squared. What would happen if you were only going 15 meters per second instead of 30 meters per second? In other words, what if you were going half the speed? Would that be half the energy and therefore half the force? Let's find out. Because you square the speed, we have to look at what you get when you square 15. 15 squared, if memory serves me correct, is 225. When I multiply that by the 1/2 m, I'm going to get EK in this case equals just 225,000 joules of energy. And since that number is going to then go in here, I'm going to get a much lower force. Think about that. By going half the speed, you get actually just a quarter of the kinetic energy and therefore a quarter of the force. Of course, the other way to look at it is by going double the 15 meters per second, you would get quadruple the energy and the force. So think about that for a minute. Because V is squared in the kinetic energy formula, every extra little bit of speed, when you choose to go higher and higher over the speed limit, translates into a lot more kinetic energy and a lot more force. So maybe you've seen signs on the road that say speed kills. You may have seen this sign before. They're trying to get you not to drive so fast. In a way, they're not wrong. I think what they mean is if you get in an accident, speed could be the thing that killed you, because not only will you have more kinetic energy and therefore greater forces acting on you when you do come to rest, but there's other things. See if you can pause the video now for a moment and think, what are the other things that make driving fast more dangerous? Okay, and you're back, and maybe you've thought of one. One of them that we studied a while back is called the reaction time. You will have less time to react to any danger if you're driving fast. So not only will any accidents be more serious, and much more serious for just a little bit more speed, but you are more likely to get into one because you have less time to react to danger on the road. So I know a lot of you are at driving age right now. You're getting your driver's licenses. Keep that in mind when you're driving, and of course, wear your seatbelt. Thanks for watching, folks. I will see you in class. Take care now.